Hey, hi friends, this is Varun Gowda. Welcome to my YouTube channel. Today we'll discuss about token embeddings. Let's consider an example. We have a sentence like I like chart GPT. Correct, right? Before feeding this sentence to the LLM model, what we have to do, we have to convert these words in this input sentence to tokens and their associated token IDs. Correct, right? These words in the input sentence are converted into tokens and their associated token IDs by using tokenization techniques. Correct, right? And we saw in our previous sessions three main ways of tokenization techniques, and we came to conclusion like subword level tokenization is the best way to do the tokenization. Correct, right? Correct, right? Let's consider this input sentence to the LLM model. I like ChatGPT is converted into token and their associated token ID. Let's say I is converted into one token and like is converted into another token and chart is converted into another token and GPT is converted into another token. We previously what we had three words that are converted into four tokens using subword level tokenization. Correct, right? Now, let's say these are all the tokens, right? These tokens were having token IDs. Let's say this is having token ID as 111 and like is having token ID as 234 and chart is having token ID as 586 and GPT is having token ID as 19. These are all the example token IDs we are considering for this input sentence. I like chat GPT. Correct, right? Now we are able to convert words in the input sentence to the numbers. Correct, right? Because before feeding this input sentence to the LLM model, we have to convert it to numbers and we have to feed it, right? Let's say these numbers, these tokens IDs, right? 111, 234, 586, and 19. Let's say we are feeding this to LLM model. LLM model for training or inference. Correct, right? Can we directly give these numbers to the LLM model for training or the inference purpose? We can't, right? We can't give these numbers directly to the LLM model because these numbers, what we are seeing here, these numbers are just numeric representation of tokens. Correct, right? These are just we are representing each token like I by 111. We are just representing the tokens with their token IDs. It's just a numerical representation. This doesn't having any meaning. Correct, right? These numbers are not having any meaning. We have to convert these numbers into meaningful meaningful numbers. Correct, right? They're just a representation. Correct, right? It doesn't encode any meaning. We have to convert these token IDs into meaningful numbers. These meaningful numbers are called token embeddings. Converting an input, converting the input token IDs into meaningful numbers. These meaningful numbers are called token embeddings. Correct, right? Okay. One more thing. These token IDs will be present in matrix called let's say token uh, for token ID 1 there will be an embedding 1. For token ID 2 there will be a token embedding 2. For token ID 3 we will be having token embedding 3. Like that, how many token IDs and embeddings we will be having? The size of this matrix will be our vocab size into embedding dimension. What is our vocab size that we used before? We said we have used the subword level tokenization, right? Approximately in GPT-3, it's around 50K. Correct, right? The exact number is 50,000 to 57. These many tokens were there in our vocab into our embedding size. Embedding size in GPT-3 is 12,000 to 88. In the sense, these many dimensions were used to represent a single token. 12,000 to 88. This is our embedding matrix size. You got it, right? This embedding matrix will be having the embeddings for all the tokens. In the sense, here we have, right, I like chat GPT and all. For all these tokens, this embedding matrix will be having the token embeddings for all these tokens. You got it, right? Now consider we have few input sentence like the first sentence like cat is eating. This is our first sentence, and we have second sentence, let's say dog is barking. We have third sentence, let's say car is moving. Like that, we'll be having billions of sentences. Let's say these words in the input sentence, right? These are converted into token IDs. Now this token IDs has to be converted into token embeddings, right? These token embeddings will be read from embedding matrix. Initially, during the start of the pre-training, this embedding matrix is initialized randomly. During the start of the pre-training process, this embedding matrix is initialized randomly. Initialized randomly in the sense, let's take an example of these three tokens. Let's say cat is one token, dog is one token, and car is another token. Let's say for cat we have an embedding of 1 to 12,000 to 88. Correct, right? 12,000 to 88 dimensions will be there. Means those many numbers were used to represent a cat. Initially, these are initialized randomly. These random values can be like 1.12, 3.45, minus 6.72 till 12,288 numbers. For dog also, let's consider we have something like 7.42, 8.62, minus 4.84, similarly till 12,288 numbers. For car, we have, let's say, embedding 4.46, 12.82, 14.72 till we are representing only three numbers here, right? But let's say it will be having 12,288 numbers. We can't write all these numbers here, right? I'm just writing some initial numbers. These are the numbers before Pre-training. Pre-training happened. Before pre-training happened. Correct, right? Now these are converted into token IDs. Token IDs can be anything which tokenizer generates. Let's say for this one token ID, let's say for this one token ID is 111. For this one token ID is 145. For this one token ID is 196. And these are converted into embeddings now. And these embeddings are coming from the embedding matrix, which is having random values initially during the start of the pre-training process. Correct, right? Now we have these embeddings for dog, cat, and car, and remaining other words or the tokens we are having here, right? For ease as well, we'll be having one embedding. For eating also, we'll be having one embedding, or it might be divided into eating, might be divided into eat and ing. These two might be divided into two subtokens, and these tokens will be having different embeddings depending upon our embedding matrix. We are giving this input, the randomly assigned initially randomly assigned token embeddings to the LLM model during the pre-training process. Now what happens? This LLM model tries to learn these billions of input sentences. Correct, right? How does this learns? It learns by generating, it learns by updating the model weights and all, right? We'll see in depth about how this LLM model pre-training and inference, everything happens in our next sessions. As of now, consider this LLM model learns all these input sentences and it generates a loss. Loss is nothing but an error. You can say it as an error. In the sense, instead of cat is eating, we are giving input sentence. If the model is predicting it as cat is jumping, now that is an error, right? It has to update this model weights during the backpropagation so that it reduces this loss or error. Correct, right? It generates a loss or error which will be adjusted during backpropagation process. How backpropagation works? It works on chain rule. We'll see in depth about how this backpropagation works, what is this chain rule and all. As of now, just learn like we are giving this billions of input sentence, and these are the embeddings for cat, dog, and the car that are there initially during the start of the pre-training process. And once we feed this embeddings to this LLM model, and LLM model starts to learn this input sentences by generating a loss, depending upon whether it's able to correctly predict the next token or next word. Depending upon that, it will generate a loss. After loss calculation, we are doing the backpropagation using the chain rule to update the model weights or parameters to reduce the error or a loss. This is what happening here. These things, the loss calculation and the backpropagation, how does it updates, and we'll see some gradient descent techniques like Adam optimizer and all. We'll see in our next sessions. As of now, consider these things. Once this pre-training has been done, these model weights are updated like after pre-training, this model weights, cat, dog, and car is there, right? These model weights for cat, let's say for cat, the model weight has become something like, I'm just taking example here, 1.81, 4.25 minus 3.98. Similarly for all 12,288 dimensions. For dog also, the updated embedding might look like 1.62, 4.45 minus 3.72. Similarly, it will be having the number still 12,288 dimensions. For car, let's say we are having something like 8.1 91, 6.42, 12.38. These numbers will continue till 12,288 dimensions. If you notice, the dimension for cat and dog were like having some distance, right? These are not similar, correct, right? These are not look similar because these numbers are not near to each, correct, right? For dog and cat. But after pre-training, if you see the numbers, the dimensions which is having values, right? This 1.81, which is somewhat near to 1.62. Similarly, this 4.25, which is somewhat near to 4.45. And these two numbers as well, right? Similarly, for 12,288 dimensions, these numbers will come near because this model, LLM model, during the pre-training process, it might have learned there is some match between dog and cat. Correct, right? So it can able to move these two token embeddings or token vectors near to each other. But if you see the car, it is a different embedding itself, right? It's not nowhere near to this cat and dog because it's completely different. These are animals. This is some machine, right? This is machine. The model has learned these two embeddings are a bit similar in terms of characteristics, and car is not similar to cat and dog. It has seen lot of examples in these billions of sentences regarding cat and dog, so it can able to come up with an embedding, updated embedding, which are bit similar. Correct, right? Let's consider. Let's consider. We'll see in depth now. Let's consider. Uh, let's consider this this cat and dog, right? After pre-training, these values became 1.81, 1.62. This is 4.25. This is 4.45. And this is minus 3.98. And this is minus 3.72. It will continue till, as I said, 12,288 numbers. As of now, we are considering only 3 dimension. In the sense, we have only 3 dimension values. Correct, right? Let's say during this LLM pre-training process, the LLM might have taken this dimension 1 as something like this dimension 1 might be representing this dimension 1 might be representing animalness. In the sense, this dimension 1 is learned like whether it's an animal or a not, something similar kind of thing. Correct, right? And this dimension 2 might have learned like whether it's an pet animal or not. It might have learned about petness. This dimension 3 might learn something like might like I'm just taking I'm doing these assumptions. No one knows how this embeddings got updated and what exactly these dimensions in each embedding represent, but if you want to assume, you can assume it like this. This dimension 3 might represent something like friendliness. Friendliness. And remaining dimensions, let's say dimension 11,000, we'll be having 12,288 dimensions, right? Out of this, let's say 11th thousand dimension might be representing whether this animal will bark or not. Correct, right? Some other dimension might be representing what food it eats. We don't know, right? What and all the data it has seen during the pre-training process, it will come up with its own new features or dimensions. According to that, it will update the embeddings. Correct, right? I think this makes sense. I hope you understood what is token embeddings and how these token embeddings will be get generated. If you like the content, please subscribe to my channel. Yeah, we'll see you in the next video. Thank you.